Well, hello there and welcome you to Mr. Robinson here, broadcasting from London with you as we've got a London football game, Jacksonville Jaguars and Miami Dolphins. It's a pleasure to have you today. I can't, that sounded a little Australian. Hello and welcome you to Mr. Robinson back here with yet another brand new exciting video on math based, of course, and as always, it's an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. If you step on inside here in London, we're going to be solving equations using square roots, quadratic equations. Now, we've been solving using factoring and the zero product property. And the whole idea was we have to set a product equal to zero because something times conceivably something else equals zero, and we need to figure out what that thing is. We can't knowingly figure out what these values are if they equal something else. But today, we're going to have quadratic equations with no linear term. There's no x, just an x squared. And that means we can have another number set on the other side as long as that x squared is isolated in some way. We can take the square root. So there's no recent video that I made on simplifying radicals. So I might have to link you to a little section on simplifying radicals, a little 3-minute bit on a video that I sent to my students regarding that if you need to see a little bit more on what simplifying radicals means. But I will be simplifying radicals without doing a major teaching on it here, if they are radicals to simplify. But let's get straight into the action, guys, and I'm going to slowly progress through them and then move on a little more briskly. As you know, I believe there are 20 problems with my worksheet that I've concocted here. So here we go. Number 1, let's solve p squared equals 9. Now I will show you the way that we did this before you knew how to solve using square roots. What we would do is we would set this equal to 0, and thankfully for this particular problem, these are perfect squares. P is a perfect square, that's p squared. 9 is a perfect square, that's 3 squared. And this is then a difference of two squares, which can factor to p plus 3 times p minus 3. This allows you to see that the solutions, if p plus 3 equals 0, then p is negative 3, and if p minus 3 equals 0, then p equaled positive 3. So one or the other. Keep these solutions in mind because I'm going to erase this, negative 3 or positive 3. So that's something that was possible to do for any solutions that are rational. Here you can solve by factoring. In this case, it was a difference of two squares. So negative 3, positive 3, right? Now, alternatively, what we can do is, because there is only just one variable here and it is squared, we may take the square root of this and be able to isolate it and make it say p equals that way. So I can take this right now, because it's isolated, I can take the square root of both sides like this. And the square root of something means what number times itself gives us that value. Now, the square root of 9, guys, is 3. Because 3 squared equals 9. The square root of p squared, you can imagine, would be p. Close. What you have to do is you have to consider, though, the fact that we were also potentially squaring a negative number. Technically, the square root of a variable squared is the absolute value of the variable, because we have to account for the fact that this variable may have been negative, and the square root of a positive is only a positive. The square root of a negative is not square root of a negative. Because this thing is a positive inside here, when you square something that's positive, we have to consider the fact that the outside has to be positive as well. So this is the absolute value of p. The absolute value of p is 3. So what does p equal? Well, then you ask the same kind of question. What can you take the absolute value of to get 3? You can take the absolute value of positive 3, or you can take the absolute value of negative 3. And I used to split these up, saying this 3 or this negative 3, whatever. I'll still split them up if I have to do further computation in problems, but for now you're going to see a lot of plus or minuses here. So p is plus or minus 3, positive or negative 3. Right there. So take the square root of both sides, and remember there were two solutions, not just 3. I just showed you in factoring there were two solutions. Consider the fact I can square a 3 to get 9, or square a negative 3 and also get 9. See, 3 squared equals 9, and negative 3 squared also equals 9. But this is the head highlight right here. Now, only for this problem and maybe number 2 am I actually going to write this absolute value step. At some point, you are going to be able to, hopefully with me, make the assumption and implication that this step has been considered and that we included the plus or minus along the way. So you can go from this step to this step if you remember to put the plus or minus, but the reason being is because squaring a negative becomes a positive, or taking the square root of a squared value is the absolute value for that very reason, that the value should be positive in the result of this, but it doesn't state what the variable could have been, positive or negative. All right, number 2. n squared equals 3. The very same thing here, guys. We can take the square root of both sides right here. Now, the square root of 3 is 3, and the square root of n squared is the absolute value of n. So the absolute value of n equals 3. Excuse me, the square root of 3 is the square root of 3. I just made a silly mistake that I tell my students to never make. The absolute value of n equals the square root of 3. Therefore, n equals positive or negative square root of 3, like that. And that's just the final result there. So like I said, guys, I am going to be skipping the absolute value step kind of here on out. So this thing right here will be ignored. I will maybe say it out loud every so often, provided that we understand there's a plus or minus that is involved. There are two answers to these quadratics, as long as you're squaring something and you have a positive result. Number 3, same thing. Let's take the square root of both sides as our b squared is isolated. So here, I'm just going to write this as b, provided that I'll be putting plus or minus right here. All right, there it goes. Now, the square root of 45, it's not a perfect square, just like 3 wasn't, but this has a perfect square factor inside of it, 9. If I turn this into square root of 9 times square root of 5, which is square root of 45, this is precious to me because I can take the square root of 9. As you know, the square root of 9 is 3, so this becomes plus or minus, this becomes positive or negative 3 root 5, like that. 3 times the square root of 5 is equivalent to the square root of 45, but it is a simplified radical. That should really be an instruction here. Simplify all radical solutions. I don't know why I didn't include that. I'm sorry. All right, but there it is, simplifying that. So like I said, I have a video. It's not really a full video on simplifying radicals only. It's more of just an intro to going into other things. But I do 3 problems there where I really show this. So if you want to see 3 more with a little more explanation on this, maybe I should link it in the description down below. Number 4, k squared equals 112. Same thing, I'm going to take the square root of both sides right here, and I'll get k equals plus or minus what? This is not 11. For those who know, the square root of 121 is 11, but not the square root of 112. This is not a perfect square. It's something that we can try and divide a perfect square out of. You know, we're considering this list here. Can we divide it by 4, 9, 16, 25, 36, 49, 64, etc.? I'd say 64 is too large because it's more than, you know, half of this. Let's start with 4. It can divide by 4 and you'd get 27. So root 4 times root 27. I'd caution you on this though for a couple reasons. Number 1, always explore and see if there are larger values, because number 2, I know there's a larger value because 27 also has a perfect square inside of it. If you only simplify this thing down to 2 root 27, you haven't fully simplified it. You've only gotten rid of a perfect square factor, but not the largest perfect square factor. So there's something larger that can factor out other than a 4. 9, no, it doesn't divide by 9, but I think it divides by 16. You divide it by 16 and you get 7. 16 times 7 is 112. 7 being not just a prime number, but really just doesn't have any perfect square factors, means that you factor out the largest perfect square possible. You can try a couple more. Obviously 25 won't work. Check out 36. It's a no-go. I think that's 108. You get to 108, 36 times 3, and 49 it overshoots by plenty. So this is the largest one here, and I can take the square root of 16 here, and I'm going to get 4, so plus or minus 4 root 7, like that. A word to the wise for those in the square root simplifying radical department, and I've taught this forever, and I still don't know how to find ways to dispel students from kind of making their own silly mistakes. Like some people would put things like 16 root 7, some people will put 7 root 4, like random things like that. My 2 things that I've really stated to students, and I want you to hear this, and I'm going to repeat them. There are 2 things. They almost sound the same. So it sounds like I'm going to say 4 things that are the same here. First of all, you don't take something outside of a square root unless you take the square root of something. And second of all, if you take the square root of something, you get rid of that square root. You take the square root out of it. So once again, and I'm going to kind of point to things where I'm making mention of that. You don't take something outside of a square root unless you take the square root of something. So when a student writes this 16, I would ask you, what did you take the square root of to get 16? And then a lot of my students will go, huh? What did you take the square root of to get 16? Why is 16 outside of a square root? The square root, and here's really the property that I'm dealing with here, guys. The square root of a product can be split up into the product of two square roots like this. That I'm taking essentially, for square root of 12, I'm taking the square root of 16 times 7. 16 is inside of a square root. 7 is inside of a square root. When a student writes something like this, I'd be asking them, what did you take the square root of to get 16? Why is 16 outside of a square root? Right? And the answer is, well, it shouldn't be. I didn't take the square root of 256 is 16. Right? Why is this thing outside of a square root? So that shouldn't be the case. It should be inside of a square root. Now, what some other students do here, you might see this root 4 here or root 4 here or something like that. I'd go, well, the square root of 16 is 4. I mean, if you put the square root of 4, then you'd probably turn into 2, or the square root of 2, even worse. The square root of 16 is 4. If you take the square root of something, get rid of the square root. Right? So those are those two things. You don't get rid of a square root unless you take the square root of something. And if you take the square root of something, get rid of the square root. Right? So those are the two things there. Kind of little things to dispel. It's really easy to do these right. Apparently, as I've taught this forever still, it's really common for students to not really understand what they're doing and to get them wrong. And that would be among the things to get wrong. All right, I'm going to move forward now, though. Let's keep going here. We're at the 11-minute mark. Number 5. Now we're going to start seeing things where we have to isolate our squared variable, where we needed to say that x squared equals. It can't have anything else interfering with it. I can't take the square root of both sides like this and expect to simplify this right here. Furthermore, I really won't want to. I need to subtract 2 from both sides. Minus 2 minus 2, I'll get a squared equals 121. Hey, there's that number here that I can happily take the square root of, but now I can take the square root of both sides, happily get the absolute value of a, or just write a, provided they put a plus or minus here. And the square root of 121 is 11, not the square root of 11, and you don't want to overcomplicate this. Something else that students do when they learn how to simplify radicals is they start to go, let's divide this by 4 and 9 and 16. No. 121 is a perfect square. If it's a perfect square, you take its square root, no questions asked. That's it. There's no root 1 here. Well, technically there is, but you don't want to write it. It's a perfect square. That's our goal. Factor out perfect square values if it's not a perfect square. And this one is right here. All right, number 6, we have negative k squared equals negative 36. You cannot take the square root of both sides right now. You can't take the square roots of negatives and expect real solutions. I suppose another math teacher can interject and say, yes, you can because blah, 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 but we're not at that level right now. What we need to do is isolate the squared variable. There's a negative 1 multiplying in front, so let's divide both sides by negative 1 here and get positive k squared equals positive 36. Now we take the square root of both sides right here, and now we get k equals plus or minus. Once again, don't overthink this, guys. 36 is a perfect square. That is 6. Positive or negative 6. And again, our whole goal here, is to our whole goal is to factor out perfect square values. Our whole goal here is to factor out perfect square values. This is a perfect square value. Our whole goal is to find out what values go into here and get you the correct answer, and there are 2 answers to that. All right, number 7, x squared minus 6 equals negative 6. I can add 6 to both sides there, and I'm going to get x squared equals 0. And yeah, you can take the square root of 0. That's no problem. There's just no positive or negative. What do you square to get 0? Well, 0. X squared equals 0. Even if this turned into absolute value of x equals 0, same thing. What do you take the absolute value to get 0? Only 0. There's no positive 0. There's no negative 0. This is one case where there's only one answer, only one solution, and that's it. Number 8, same thing, only we add 12 to both sides, and it looks like we have a radical worth simplifying here. B squared equals 96. 96 is not a perfect square. Let's go ahead and take the square root of both sides, however, and we'll get b equals plus or minus. I can divide this by 4 and get 24. I cannot divide it by 9. I can divide it by 16 and I can divide it by 16 and get 6. And I think that's the largest one there as far as perfect squares go. Again, I chose 16 because it is a perfect square, because I can take its square root. So let's check that out. And really what you ask yourself, so that's plus or minus 4 root 6. What you ask yourself here, if it's fully simplified, is Can I factor out any perfect square values out of 6? Can any of these numbers divide out from 6? And you notice I didn't choose 1 here. All of these can divide by 1, but it doesn't reduce the value, so it doesn't further simplify it. So you notice I'm not choosing those ones. All right, number 9. 4k squared plus 9 equals 13. If I subtract 9 from both sides, I have 4k squared equals 4. Now, it's possible to take the square root of both sides from here. I do not recommend it, and I'm just going to state it right now. Like, I'm just going to say don't. Don't, especially if this was not a perfect square, which it is. But there are properties that people don't pay close enough attention to with this. Isolate your squared variable, not just the term. Divide both sides by 4 here. 4 over 4. You get 1k squared equals 1. Please isolate your squared variable or squared quantity. Move everything else over. So let's take the square root of both sides now, and we get k equals plus or minus. And 1 is a perfect square, even though I didn't list it. The square root of 1 is 1. So positive or negative 1 goes into here. And always check these things. 4 times 1 squared plus 9 and 4 times negative 1 squared plus 9. You still get 4 plus 9, which is 13. All right, number 10. 9 minus 11v squared equals negative 200. I'm going to first subtract 9 from both sides here, and you will still have a negative 11v squared here. And then you'll have negative 209. Even I don't know what 209 divided by 11 is, or negative 209 divided by negative 11. But I am going to divide by negative 11. And mentally here, we got that 121 plus 88. So 11, 19. I should have assumed that with the 9. So v squared is 19 here. So we take the square root of both sides, and you get v equals plus or minus. And people will fight hard to try and simplify a radical. You have to understand that some radicals just can't be simplified, just like the 3 here, or just like anything else that was left over, the root 7, the root 6, or the root 19. 19 is a prime number in and of itself. It definitely can't be simplified. But some numbers, and some large numbers even, just don't have perfect square factors, and we're going to have to be accepting of that. But that would be the final answer there. All right, so there we go. Number 11, we're halfway through. We got 15n squared plus 14 equals 10,094. If I subtract 14 from both sides, I'll get 1080. Someone wants to whip out a calculator. I'm going to conventionally get to this. 1080 divided by 30, 108 divided by 3 is 36, so 72. So 720. 720 is my thought on that one there. I believe that's correct. So square root of both sides there, and I'm going to get n equals plus or minus. So there are bigger, numbers at play here, like significantly bigger, potentially. If you have trouble finding the largest one or don't want to go that big, like, I know that I can divide it by 9, and I'll get root 9 times root 80. This could be one of those things. Okay, now I know something bigger. I know something bigger it can do. But let's say you didn't. Let me start with this. Let's say you didn't. And I was like, all right, I'm going to at least do 9. I know it can do that. So I get plus or minus 3 root 80, but just because it can divide by 9 there doesn't mean you're done. You want to consider the fact that 80 can still be simplified. So what would you do in this case? Now you take the 80 and you break that down. So root 80 turns into root 16 times root 5. That would be like the largest value to divide out of that. Or you could do 4, but then you'd have to keep going another step. So the square root of 16 is 4. So here's what happens here. Everything here is multiplying. 3 is multiplying by 4. The square root of 16 is 4, and you get root 5 there. So this becomes plus or minus 12 root 5, like that. I want to make sure I didn't screw anything up because I expected a different... Oh, there's something even... Wait. No, wait, hold on. Is it 12 root 5? I'm drawing a blank here suddenly. Let me do it the other way I was going to do it. Oh, wait, maybe it was. Oh, there's something even larger than the number I was thinking of. So I was thinking I could divide this by 36, which I can. If I did 36, excuse me, take the square root here. Here's an alternative. If I divide this by 36, I get 20. Hey, 20 can still simplify. That means there's something even larger. You know what's larger, I think? I think 144. And actually I know 144 because this 12 here, now that I've done that, you can go even larger here. You can try large perfect squares. And yeah, you can do 144, and 144 times 7 is times 5. So I keep forgetting this is here. Of course, the 5. So square root of 144 is 12. So you go plus or minus 12 root 5. So once again, my suggestion to you is, well, it's one of several things. If the number's too large for you to consider testing over and over and feeling like you're wasting more time doing it, you can do something like this, provided that you understand you got to still keep simplifying a radical. Just work with that the way that you can best make sense of. It'll take more than one step, but it might take less time depending on what you're doing. Otherwise, go through, and I'm going to write this one more time, and I'm going to kind of get rid of it after. But go through your perfect square factors. Go through your perfect square factors and try and divide everything under the sun that is logical to consider dividing. And do it until the other factor that you divide it from no longer has a perfect square within there. So let me go up to 16 squared just to kind of give you the idea. And I think I chose ones here that could only go up to 12 squared. So 144 was the max here. But, go through these numbers here and keep dividing out factors until your other value is no longer containing perfect square factors. So when I divide by 9 and I get 80, maybe you realize that 80 has perfect square factors in it, like 4 and 16. And if you say, okay, well, that has a perfect square factor in it, that means this isn't the largest value it can divide out of. So again, you have two options. Either simplify this further or try a larger perfect square factor. And then you try 16. I suppose it has 16 because 80 has 16. You try 16, you figure out it has a larger. 25 doesn't work. Like I said, 36 worked. But then I recognized, 20 has a perfect square factor of 4, right? And then I don't know which ones it has until 144. And then you have a 5, which doesn't have perfect square factors. That means 144 is the largest perfect square factor I can take out of it, which means there's only just kind of one step from there. And what I'll probably start doing on the next page is I probably won't be writing this step, guys. I'll probably say I got 144 and 5, and the square root of 144 is 12. If there are students who can act more efficiently and get things correct, I don't mind you doing that. But you got to remember what happened in between, that this turned into that. I'll say it out loud. But the whole, wait, where did the square root go? I took its square root. All right, I lived on that problem for a little while there. Let's continue on to number 12. Number 12, 49x squared, plus 11 equals 20. If I subtract 11 here, I get 9. Okay, now I'm going to get x squared equals 9 over 49. Now, here's an interesting bit. It's a fraction. And we can't reduce it, which is fine. I'm going to still take the square root of both sides, though. We have the property that the square root of a product equals the product of two square roots, like this. It's also true of fractions. The square root of a fraction is equal to the fraction of two square roots. And I'm not saying it's better left unsaid, but those who do know that division just means multiplication by a fraction, that this has to be true. If this is true, then this has to be true as well. Both of them, because, what if I just turn this into 9 times 1 over 49, and then I'm just taking the square root of one and the other. I guess it's still a fraction within, but yeah, it has to be true there. So basically what I'm doing in this case, guys, is first of all, I have a plus or minus, but I'm taking the square root of 9, and I'm taking the square root of 49 right there. So that's what's going on in that problem there. So the square root of 9 is 3, and the square root of 49 is 7, and you get plus or minus 3/7 there. And many here do know that when you square a fraction, that you square the top and bottom as well. So if I take 3/7 squared, that is 3 squared over 7 squared. So it only makes sense that the square root does the same thing as far as, I don't want to say distributing the square of the square root, but applying the square to the square root, taking the square or the square root on both the top and bottom, just like we would a product. And there we go, plus or minus 3/7, there's a fraction answer. All right, let's go ahead and go to that backside, and there are 8 more problems here. Now, what's going to happen that's a little different, not significantly so, there's more steps will be involved eventually, but what's a little different here is now we have a squared quantity, where the variable is squared, and, you know, if we did this in the past, what I'd be recommending, because you wouldn't have a square root method, is you'd be literally squaring this. Like, I started off with a problem that actually has rational solutions, which means this is factorable if you break everything down. So one way I would have done this in the past here, before this video, before this lesson, is I would have squared this whole thing. Not squaring this and this, but actually doing a perfect square trinomial, where you square the first term, you double the product of both terms there, and then you square the last term like that. And that's something that, by the way, you have to know what this looks like for the next video I do on completing the square, and that it breaks down to this. So I think it's worthwhile that I'm showing this in the first place. Equals 196, and then I subtract 196 over, and I get b squared minus 16b minus 112 equals 0. I think that's 112. No, 132. 132 equals 0. And then you factor, right? I subtract this over because this is where I would use zero product property, because this is no longer a product. And if I factor into a product, it's no longer a perfect square product. So this is something I would have done in the past. What two numbers multiply to make negative 132 and add to make negative 16? I think 6 and 20, yeah. 22 and 6. And so you get b equals 22 or b equals negative 6. And, you know, I'll keep this on the side. This isn't the way I'm asking us to do this. We're going to solve using square roots. This one probably took significantly longer considering how the problem was initially set up. But let's remember these two solutions here. And notice it's not just a plus or minus, same value. Now that this is a squared quantity, this negative 8 is affecting things after that squared portion is kind of taking hold. So let's keep that one in store there on the side. I'm going to leave it like that. And let's continue this the way we would before. Because the quantity is squared and isolated, I can happily still take the square root of both sides. There's no problem with that. The b minus 8 is squared. It's b minus 8 times b minus 8. So the square root of that is the absolute value of b minus 8. But of course, I will leave it as just b minus 8, provided that I put the plus or minus here. 196 is one of those perfect square values. Okay, I do go up more than 12 there, and that is 14. So positive or negative 14. Now, I'm not finished with this problem, though, because I have to solve for b. I have to add 8 to both sides here. So when I add 8, and every teacher is going to recommend this here. When I add 8, I'm going to stick it in front. I want to make this as positive 8 plus or minus 14. So you are actually adding 14 from 8 to 8 or subtracting 14 from 8. This is a logical time, though, for you to perhaps split this equation into two. I want to actually compute these two values to say that b either equals 8 plus 14 or b equals 8 minus 14. That plus or minus literally means adding or subtracting, positive or negative. So 8 plus 14 is 22, or 8 minus 14 is negative 6. And we get those same answers there. And I would argue this was still a more handsome version to solve for than this was, getting all the squaring that, subtracting that over, and actually factoring to get it down. That when you have this squared quantity, this is recommended that you work with. And even if it wasn't recommended for this problem, what you have to keep in mind when we look at a problem like number 14 is sometimes you can't factor. I'll let you know right now, number 14, if I'd used this method here on number 14, I would get something that is non-factorable. This one, I happen to choose rational solutions for you to set up a situation where we say, let's try this out. Not all of them work that way. Not all of them work that way. Not all of them are factorable like that. So this one is not. Number 14. This is where I do have a squared quantity, and I will take the square root of both sides. You know how I know it's not factorable? Because once this is isolated over here, when I take the square root of this, 78 is not a perfect square. It's not a perfect square. And you know what? I don't know if 78 has any perfect square factors in it. You divide it by 2, you get 39. 78 breaks down to 2 and 39. 39 breaks down to 3 and 13. Square root of 2 times square root of 3 times square root of 13, all prime factors, no duplicates, means there are no perfect square values in 78. That's an example of a large number, a composite value even, a composite value that has no perfect square factors. That just means that it stays as the square root of 78. I don't simplify it further. So this is x minus 5 here, and this is plus or minus the square root of 78. And that's it. It's irrational, but it doesn't simplify. And now I'm going to add 5 to both sides, and we'll get x equals 5 plus or minus the square root of 78. And you know what? That's your answer. And I say that in singular form. Those are your answers. This is 5 plus the square root of 78 and 5 minus the square root of 78. If you were to approximate, 78 is close to 81. The square root of 81 is 9. So this number is a little less than 9. It's kind of like 5 plus 9, which is a little close to 14, and 5 minus 9, which is a little close to negative 4. This number, these two answers are kind of 13.9-ish and maybe negative 3.9-ish. I don't know what they are exactly, but that's what they're about. That's what the answers are. But these are exact answers. This is as simplified as possible. And again, I stuck the 5 out in front when I added it over. I would prefer not to put positive or negative root 78 plus 5. There are kind of a lot of things to this that make this icky. Among the reasons that when we start using what's called the quadratic formula, you're going to see things appear in this form as well. So once again, guys, when you add this thing over, I recommend you stick it in front. It's a better notation to work with. It helps. I'm speaking beyond what you guys know, but it helps understand conjugates better. When we use quadratic formula better, it's just a cleaner, more accepted version to write. And I really do. I almost require it for my students to write it, even though the right answer would be true if you did positive or negative root 78 plus 5. I just wouldn't. All right, number 15 here. We have to isolate the squared quantity still. Even though this might have rational solutions, I don't think a lot of people are going to want to go the route of 4a squared plus 20a plus 25 minus 100. I don't think people want to factor with a 4 and things like that. And, I'm not asking us to do that right now anyway. Let's please proceed. So let's add 100 to both sides. We have to still isolate the squared quantity. We still have to get this part by itself. And it's okay that it's not equal to 0 because it's the same thing times itself, equaling our value. That's where we can take the square root of both sides. Now the square root of 100 is 10, which is good. This is 2a plus 5 equals 10. No, plus or minus 10. Don't forget that part there. So now I'm going to subtract 5 over, and this is where, once again, you're going to want to really consider splitting your equations up here in a moment. I subtract 5 over, I'll get negative 5 plus or minus 10, okay? And this is where you either, I don't know if right here you want to do it, or if I divide by 2 first. I'm trying to think of what's a better approach. I guess now splitting it up is pretty fine here. So I split it up into either 2a equals negative 5 plus, let's see, I'm trying to think if that's how I would generally do it. You know what, let's do this first. Let's not split it first. I am going to divide both sides by 2. If I divide both sides by 2, I get a equals negative 5 plus or minus 10 all over 2. Again, I can't think about which way I generally do this. If at this point it's split up, I don't know. Anyway, I am going to split this thing up because I can actually do negative 5 plus 10. See, this one here, I couldn't simplify this further. There's nothing to combine or anything else. I just leave it like that. But I can do negative 5 plus 10. I can do negative 5 minus 10. So negative 5 plus 10 over 2, yeah, I think I do it this way. Or a equals negative 5 minus 10 over 2. So negative 5 plus 10 is 5. So that's 5 halves. That's one answer. And a equals. Or negative 5 minus 10 is negative 15 halves, like that. And you know what? You leave it like that. Those are your two answers. 5 halves and negative 15 halves. Sure, it's 2.5 and negative 7.5, but there are some answers that won't be exact if you write it as a decimal, and we aren't going to bother with mixed numbers there. Improper fractions are totally cool. Just make sure you reduce the fraction if you have to, if you can. All right, let's keep going here. We have number 16, and I have 2x plus 3 quantity squared minus 15 equals 9. Same thing, guys. We got to get this thing by itself. I'm going to add 15 over here. 2x plus 3 quantity squared equals 24. Now when I take the square root of both sides here, I get 2x plus 3 equals plus or minus, and the square root of 24. This is one of those instances where I'm going to simplify mentally with you. This is root 4 times root 6, right? The square root of 4 times square root of 6. And I chose 4 because it's a perfect square. I can take its square root. So root 4 times root 6. The square root of 4 is 2. So this becomes 2 root 6, like that. Okay. So I'm going to subtract 3 over, and I get 2x equals negative 3 plus or minus 2 root 6, like that. And these cannot combine. You got to treat the 6 just like a, just like a z. Negative 3 plus or minus 2z. I can't combine those two things. I can't combine these. That's not a 2, guys. It's 2 times the square root of 6, whatever that number is. And you can't assume that negative 3 plus 2 would, make things the same. So you got to keep that the same as it is, and I'm going to divide both sides by 2. So when I divide by 2, everything here divides by 2. Negative 3 divides by 2. 2 root 6 divides by 2. And you know what? I leave it like that. There are times where this thing can simplify. I don't remember if we run into any in these cases here. You're going to have to be careful if they do. It's one of those strategies that students, I'm going to have to work with students on, and I'll explain the best I can. But what you do not do is you do not cancel these 2's right here. The main reason, and I'll get to it when we do redo something properly, if we need to, is because the negative 3 is also dividing by that same 2. You can write a version where you split up this negative 3 halves and then divide this by 2, but these are all over the same fraction, so I can't just divide this unless 2 is a common factor in both terms, which it's not. So I'm going to leave it like that. And we're taking care of. That's your final answer. And look, those are your final 2 answers. There are 2 answers to that. They're interesting, they're different, but that is what they are. You can approximate them. If you use the calculator, you can approximate what they are. I don't know roundabouts what they are really, and that's okay. We got exact answers. That's what we're working for. And if we graph them someday, then great. All right, number 17. If this was a word problem with a model and something, then I'd be happy to use a calculator on that. All right, number 17. 7 times b minus 1 quantity squared equals 112. Same kind of deal, guys. This is not yet a squared. The squared quantity is not yet isolated. The 7's in the way. I want to divide by 7 happily. And 112, we've seen this 112 a couple times. I think that's 16. 112 over 7 is 16. So b minus 1 squared equals 16. We take the square root of both sides there, and we get b minus 1 equals plus or minus the square root of 16, which is 4. So b equals 1 plus or minus 4 when you add the 1 over. Now, again, I'm not done here because 4 being a perfect square means you can actually add 4 or subtract 4. And so you get b equals 5 or b equals negative 3. And you really want to split the equations. Some people might assume that it's like, oh, b equals plus or minus 5. You're like, oh, 1 plus 4 is 5, so therefore 1 minus 4. No, it doesn't work like that. 1 minus 4 is negative 3. So, you really want to split it up. It's not a plus or minus answer anymore. As far as when you clean it up, the 2 values, their absolute values are different in those cases here. And they always will be. As long as it's a squared quantity and not just a squared variable, you are going to get 2 different numbers, not just a plus or minus of something. All right, let's try this thing again. Divide both sides by 5 here, and now we're going to get n plus 4 quantity squared equals, I think, 40. So now we take the square root of both sides there, and now we're going to get n plus 4 equals plus or minus. So this divides by 4, and you get 10. 10 doesn't have any perfect square factors, so root 4 times root 10. It looks like that's the smallest it goes, and the square root of 4 is 2. So you get 2 root 10, plus or minus 2 root 10 there. And again, you might ask, where did the square root go? I'll tell you, I took the square root of 4. Right? I took the square, right? You don't get rid of this square root unless you take the square root of something. I took the square root of 4 to get to. 4 times 10 was 40, and that's where it came from. Subtract 4 from both sides, and I get negative 4 plus or minus 2 root 10. Again, bring that negative 4 out in front, please. It's highly, 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 highly recommended. And, there's nothing else I can simplify there, okay? That would be my final answer. That's, that's as far as exact answers go. That's the best exact answer you can write, period. An answer key would say the same thing. All right, 2 more problems, guys. We're almost done here. This problem doesn't look any harder, actually, than the previous one. So, number 19, we divide 12 from both sides here, and we're going to get n plus 2 quantity squared. I want to keep consistent. Let's use green. N plus 2 quantity squared here equals 4. I'm going to take the square root of both sides without drawing the square root symbol. Let's see if you're comfortable with that. N plus 2 equals plus or minus 2. You guys know how I did that? Took the square root of that side, and that's gone. Absolute value of, or if I don't write that, that's because I put plus or minus here, and square root of 4 is 2. Right. There are some little things like that, like me personally. You're diving pretty soon into this is how Mr. Robinson would do it if he was on his own, not teaching anybody kind of thing. And if that's something that you'd ever feel comfortable with someday, then you can work that way. So, but I would definitely write this step as well. Now, here's what I would tend to write next. I would actually calculate these in my head without doing this next part. So, without doing the, like, I'm going to write this or that, but I'm not going to write -2 plus 2 or -2 minus 2. I'm just going to calculate -2 plus 2. So anyway, I subtracted 2 over, guys. Here's that one right there. And then the plus or minus 2 is right there. So what's -2 plus 2? It's 0. What's -2 minus 2? -4. So that, ladies and germs, is, despite the fact that it took me longer to do it, this would have been the Mr. Robinson steps method. This is how Mr. Robinson would have written out the problem. If there were too few steps written, if you're like, wait a second, I need this, I need this, I need this, I need, this, then okay, yeah, if you need all those steps along the way, go ahead, you're fine. But this would have been the Mr. Robinson go-to, just so you're aware. Let's see how easy or difficult this one will be with everything. So we got several things to work with here. Obviously, save the best for last, right? Number 20. Don't divide both sides by 3 just yet. I'm sure it's possible to do, but make sure you subtract this over. Subtract the 45 over first, and we get 3 times 3x minus 8 quantity squared equals 36. And then I divide both sides by 3, and I get 3x minus 8 quantity squared equals 12. So let's take the square root of both sides, shall we? Are you comfortable with me not drawing the square root symbol? I don't know. Go ahead and draw the square root symbol if you need it. The square root of 12, guys, is 2 root 3. Square root of 4 times square root of 3. So plus or minus 2 root 3 there. All right, we got 2 more things to go here. I have to add 8 to both sides. 8 plus or minus 2 root 3. And then I divide both sides by 3. And I get x equals 8 plus or minus 2 root 3, all divided by 3. Once again, these would have been the Mr. Robinson steps of go-tos and things he, I guess, would have skipped along the way. And that's the final answer. Now, we are done. We are done. I do want to state that it looks like I left these kinds of problems out here. Let's say hypothetically, because this is the correct answer, but let's say hypothetically that instead of this being a 3, let's say that this was a 4. I'm going to state for a moment, guys, let's say that this was a 4 right here. There would be more to do in this case here, because 8 can divide by 4 and 8 fourths can reduce, and 2 fourths can also reduce. I imagine I'm going to be doing other videos or other tactics with my students and helping them reduce these as we go forward. Probably not just its own lesson, but in terms of simplifying radicals. What you do is you find the greatest common factor of 8, 4, and 2, and you divide that among all of these values here. These can all divide by 2. So 8 over 2 is 4, 2 over 2 is 1, and 4 over 2 is 2. And this would have been 4 plus or minus 1 root 3, all divided by 2. And that would have been a reduced answer of this if that number was a 4. Hypothetically speaking, that number was not a 4, but here's an example of canceling things out and reducing things. You have to do it to every term in existence on the top there, because 2 would have been a common factor. In the other case, there was another number that was not a common factor, and that wouldn't have happened. But this is how it would have been simplified. So just a little tease, guys. Look forward to those coming in the future. But of course, this was not a 4. It was a 3, and these do not have a greatest common factor that's not just 1. So that's your final answer there. All right, guys, that'll be it. Thank you so much for watching. This is Mr. Robinson, and I appreciate you coming into my virtual classroom here. We're here in London. And thank you so much. Take care. Bye.